Hi, everybody. If I'm looking off screen, it's because I have two monitors, and for reasons I don't fully understand, the presentation insists on being on one monitor that is not the one that my webcam is on. So uh, forgive the lack of eye contact. Welcome to the first of two sessions on the topic of causal inference for empirical ecologists. This is a topic that you can certainly go off and read a lot about, but I thought it would be useful to try to communicate it in a way for people like us, for those of us who are coming to this topic, not because we grew up wanting to be statisticians or mathematicians or something, probably not even because we grew up wanting to be theoretical biologists of some kind, but we probably grew up catching bugs and pressing flowers and liking being outside. And then it came, I think, as a bit of a shock to all of us when we realized that we actually hadn't run away from math. We ran right into its waiting jaws as ecologists. And the reason I like to teach this is because I find it profoundly encouraging to reapproach the kinds of problems that we run into from the perspective of causal inference, because that prioritizes our knowledge as empirical ecologists again. It puts us back in the driver's seat of our own research. At the outset, though, I want to take a moment just to talk about causation as such. I want to call your attention to the picture that I've chosen. This is going to be a theme throughout this talk. This is a mixing console. It's the sort of thing that sound engineers use at a concert or some kind of public venue. And the way it works is there's a bunch of sliders and switches and such, and each of them has some effect on the sound that the audience hears. Causation as such is a very deep and vexed philosophical topic that we won't be able to go into very deeply here. That's not the point. But I want to offer a pragmatic definition that works well for practicing scientists, because it is very something we can operationalize. And that is that something is a cause of something else if intervening on the cause changes the value of the effect. So X causes Y if intervening on X changes Y. So I want you to have this image of the mixing console in your mind. The cause is what you're sliding or switching, and the effect is what comes out. It's the sound. This is both a very fitting illustration of how the kind of causal inference that we're going to talk about today works, and an illustration of the intrinsic limitations of this approach, which we will revisit at the end. For an outline, though, I want to start by talking about why causal inference is worth thinking about. I'm not actually going to talk about Aristotle, but it seems inappropriate to talk about causation without at least showing a picture of him. I'm going to introduce you to a specific tool called the directed acyclic graph, or DAG. And then we're going to apply this tool. We're going to use DAGs for variable selection. We're going to use DAGs for parameter interpretation. And then I'm going to talk briefly, and more briefly than I would like to, unfortunately, about DAG validation, which is very important, but it's not going to be a focus today. And then I want to end by discussing the limitations of DAGs. I don't want to portray DAGs as a silver bullet. They are a helpful tool. And we'll talk about their limitations. All right. So why causal inference? This may be a new term for you, or you may have heard it crop up now and again. Maybe if you've gotten into something like structural equation modeling, the language of causal inference is something you've heard before. For me, though, it was not something I was taught. It was not something I was taught as an undergraduate. It was not something I was taught during my PhD program. And I think it is a little bit outside of the mainstream vocabulary for most practicing scientists. And I think this is a problem, because we really need to understand science as the study of causes in a broad sense. One one reason that is important is that we really, look, like I said, we got into this for a reason, right? We became ecologists probably because, like my daughter here, this is from several years ago now, but she has her pet praying mantis here. Uh, like she's not interested in this praying mantis because she wants to predict it, like somebody predicting stock prices or weather patterns or image recognition or something like that. This is not a there is a love for the world behind what we're doing, right? We want to understand it because it's good and beautiful and we're drawn to it. Um, so we have a higher goal than just prediction. Um, Also, though, especially as ecologists, we often want to understand so that we can intervene, right? This is applied ecology, this is conservation. We want to make informed interventions. Only causal understanding can guide intervention. Prediction alone cannot. You need to know what happens when you take that slider and you move it up. Um, and this also goes for predicting under novel conditions, right? If you have a predictive model that's trained under a certain set of conditions, it may perform very well until the context changes. And of course, the context is always changing. Think of something like global warming, or land use change, things like that. Um, we need to understand causes to guide intervention and to do prediction even under new circumstances. Even when we think all we're doing is the humblest empirical description, even that requires a causal understanding of the data generating processes behind what we observe. For example, this is one of those trap nests. I'm sure you've seen them. This is from a study that I attempted that went rather badly because nothing nested in them. But these are not unbiased samplers of bee communities or wasp communities. There's a reason why the things that show up in them show up there. And there's a reason why the things that don't show up in them don't show up. And if you don't understand those causal processes, you can badly misinterpret the results that you get. Causal inference puts science before statistics and it puts humans before computers. And I want to dwell on this for a little bit because honestly, this is the crux of the matter for me. This is why I love to teach this stuff so much. I find what often happens during the course of a PhD program is that students start program, don't really know what they're doing yet. They're new, their confidence level's not so high. They get thrust out into the field and they have to start measuring things. But when you're out in the field, you gain confidence. And by the end of the field work, you're feeling like a real field biologist, right? You know all your study sites, you know the organisms you're sampling, you have a feel for the ecology. You feel like a professional. Then, though, the field season ends and you come back and you're like, oh no, I have to process samples. And that's tedious, but then the real trouble starts when you realize that you're kind of running out of time and you really better start with the statistics. And then everything falls apart, right? All of that confidence that you built up, you feel like you have to check all of your biological expertise at the door, right? And walk into this realm of statistics where you pretend that you don't know anything about biology, when in fact you do know a lot about biology. Well, you don't know anything about statistics, but you have to kind of flip that in your mind. Um, and then you start grinding away at methods you don't understand, just trying to get the darn things to work under the lash of running out of time, running out of funding. And then before you know it, you have to start writing something, right? And this is a demoralizing process that empties you of a sense of expertise, and you feel like you're just a servant to these mindless algorithms that you're just trying to get to run until you finally torture out of them something that you're able to write about. This is not how science should be done. This is not the experience that you should have as a student or in any other stage of your career. We can do better than this. All right. As I said, I think the way to do better than this, one of the ways, is to focus on causal inference. And one of the best tools for that is called the directed acyclic graph. So I'm going to start by introducing the tool, and we're going to kind of dissect it a bit. I want you to have some familiarity with it. And then right at the point where your eyes are probably going to be glazing over because it's so abstract and there's nothing but letters and arrows and stuff, I want to shift into doing more concrete examples where the variables have names that you will recognize, and I hope that it will make good sense to you. All right, I also wanted to introduce this by way of the people who introduced it to me. So these methods were developed by Yuta Pearl. This is a book of his that I recommend. It's not too technical. It's not the most accessible thing, but it's short and it's an attempt by statisticians to be accessible. So they're doing their best. DAGs were very much popularized though by Richard McElraith, who's the best teacher of statistics you will ever encounter. I cannot recommend his work highly enough, especially his lecture series called Statistical Rethinking. It's on YouTube. Please watch it. I included links in the material that I shared with you. Also, there's a book of the same name, which is very good, but maybe start with the lectures. And then recently, Suchinta Arif has become a big advocate and early adopter of these techniques in ecology. And I think this makes her work especially important for us, because finally, here's somebody writing about these techniques for people like us. And the examples are things you will understand. The language is very accessible. And this is somebody actually doing in ecology what I'm calling for us to do. So I highly recommend her work, and especially this paper to start with. All right, but let's talk about DAGs. Now, already you may notice that things have gotten a bit abstract. We have letters, we have circles, we have arrows. Don't panic. Let's take this one step at a time. A DAG consists of these components. We have endogenous variables. So endogenous just means internal. So it's inside the system. These are the things that you measured, or at least you're thinking about them. In other words, there are things that have explicit causes in their cause variables in your causal model. Not in the world, this is a different question, right? But in the little world of your model, they are caused by something. And these can be further classified as a variable we can call it a treatment or a predictor. This is the variable whose causal effect you're interested in estimating. We'll come back to this. There's often only one variable that whose causal effect you can estimate at a time. So we need to get out of the habit of thinking we throw everything into a model and interpret everything the same. That's not how it works. And then there's an outcome. So typically I'm going to talk about X and Y as the cause and effect. And then there's some set of covariates. Here is just one, but it could be many covariates. And these relate in some way to the treatment and the outcome. Importantly, all of our endogenous variables are caused too, but they're caused by things outside of our system, called the exogenous variables. Typically, we don't depict these in DAGs, so you'll see me drop them later on. But bear in mind that everything has a cause. That's one of the assumptions we're working with here. Just because you didn't measure it doesn't mean cause doesn't exist, right? And most importantly, though, everything in a DAG is connected with arrows. These are the causes. And in DAGs, they're called directed because causation flows with an arrow in the direction the arrow is pointing. And they are called acyclic because you're not allowed to have loops. You're not allowed to have cyclic causation, which is to say you're not allowed to have feedback. And this is a major limitation that we're going to get back to at the end. But just accept it for now. There are some kind of hacky ways of dealing with it. But for now, just accept that it has to be acyclic. And as I said, we typically don't depict these exogenous variables when we're presenting DAGs, but don't forget that they're there. Now, for any DAG, this is a very simple one. You can imagine a very complex one, though, and I'll present a slightly more complex one soon. You can identify three basic causal structures. Every DAG is made up of some combination of these structures. First is and I should say that the names of these structures, the chain, the fork, the collider, they are based on the role of the covariates or the covariate in relation to the treatment and the outcome. So the first of these is called a chain. It's when the covariate is a mediator between the treatment and the outcome. The second is called a fork, where the covariate is a shared cause of both the treatment and the outcome. And the third, the most sneaky, is the collider, where the covariate is a shared effect of the outcome and the treatment. Now remember, causation flows with arrows. It doesn't flow against arrows. So in the chain, it flows from X to Z to Y, and the fork, it flows from Z to X and from Z to Y. And the collider, it flows from X to Z and from Y to Z. But, this is important, information flows both with and against arrows. And by information, understand quantitative association, something like a correlation. If this is a little confusing, it doesn't have to all make perfect sense. Just try to flow with it for now, and we can circle back around if necessary. So information flows against arrows unless it is blocked by conditioning or by a collider. Now, what conditioning means is including the covariate in your model. This is how multiple regression works. This is often misunderstood, but when you include covariates in a model, the estimates you get for everything else are conditional on a kind of virtual experimental control of covariate. It is fixed at a certain value. Typically, it's mean. So if you condition on it, that blocks the flow of causation and it blocks the flow of information too. A collider is the opposite case though. This is very important. If you condition on a collider, if you include it in the model, that actually opens the flow of information and messes up your causal inference. So you don't include a collider in your model. It's already blocking the flow of information. Again, this doesn't have to make perfect sense. Just go with it for now. So let's start with the example of the fork. And let's say our goal is to infer the total causal effect of X on Y, right? We'll get to concrete examples in a minute, but to do this, we need to open the flow of information along all causal paths. So all the paths that are flowing with the arrow between X and Y need to be open. In this case, there's only one causal path between X and Y, and it's this direct path here. And importantly, we need to block the flow of information along all non-causal paths between X and Y. And the non-causal path is this fork, Z here. It's not causal because to go from X to Y via Z, you have to go against the arrow here. But information is still flowing if Z is not included in the model. Z functions here as a confound. This is a classical confound. This is probably something you have encountered in a stats course at some point. So in this case, in the case of a fork, we need to condition on Z to block that non-causal path and get an unbiased estimate of causal effect of X and Y. Now let's consider a chain. The task is the same. We have to open all the causal paths and block all the non-causal paths. But in this case, there are no non-causal paths. There are only causal paths. Both of these paths are causal. If we include Z in the model, we actually block part of the causal effect of X on Y. We create a bias in our estimate by including Z in the model. Okay? It's the difference between a chain and a fork. Now the collider, as I said, is the most counterintuitive one. The collider already blocks the flow of information when it's not included in the model. If you do include it, it actually opens the flow of information and creates a confound. It creates bias where there wasn't bias to begin with. So in this case, we do not include the collider, the covariate Z in the model, and we isolate the causal effect of X on Y. Okay, if your head's spinning a bit, that's okay. It takes a little practice to think about problems this way. But realize that what we're doing here is we're taking a conceptual problem and we're turning it into a visual problem. And I think in general, whenever you can do that, it's a good idea because your brain is better at visual problems than conceptual problems. So short takeaway here is always draw pictures. The more pictures you draw, the better you'll understand what you're doing. DAGs are just a very specific type of picture. All right, now, that's how DAGs work. That's the logic of using DAGs to infer causal effect. Now, let's see how this works out when it comes time to do something that I think is the most vexing problem that students, really just empirical scientists in general, encounter in the course of statistics. And that is variable selection. We have an R club at Würzburg. I don't know if you have clubs like that at your institutions. It's a wonderful thing. I think you should have one. If you don't have one, start one. But I think it's safe to say that the topic that emerges with the highest frequency and with the greatest sense of desperation behind it is how to choose variables in a model, right? Part of this reflects some kind of bad methodological habits in empirical ecology. I think we tend to not do enough planning and then do both too much and not enough measuring, and we have to go back and sort out that mess statistically, and that's not ideal. But by this point, you have the things you measured are measured. You're not going to measure anything new. You have to make decisions about them. And for those of us in empirical ecology, this is hard work because for the most part, we don't do experiments, right? I would venture to say that many of us in the room have never done an experiment as ecologists. Because experimentation in ecology and field ecology is just so hard as to be almost impossible. What we do is observational studies where we measure things and then we attempt to, and this is correct, we attempt to create virtual experiments through statistical control to make valid inferences. But the point of this lecture is that those inferences are only valid when they are causally valid. So how do we do variable selection in a causally valid way? I like this painting, and I want to just read to you the full title of the painting. It has a very long title, but I think as I read the title, the reason I chose it will become obvious to you. The alchemist, in search of the philosopher's stone, discovers phosphorus and prays for the successful conclusion of his operation, as was the custom of the ancient chemical astrologers, by Joseph Wright of Derby. This is what variable selection often feels like, right? The not guided by any real process. The best you can hope for is to discover phosphorus while looking for something else, and then think, oh, God, please don't let this be wrong. Like that is how variable selection feels, does it not? We can do better than this. First, we need to talk about some things not to use for variable selection. I warn you, this may be a little troubling because I can almost guarantee that you've all used these things for variable selection because I've used all these things for variable selection. We are all in the same boat here, but let's have the courage to criticize ourselves. One thing not to use for variable selection is p-values. I'm not saying this because I have a preference for Bayesian statistics, though I do. There are other kinds of critiques that could be made about p-values, but this is something that frequentist statistics completely agree on. In fact, there is no living or dead statistician that I can think of who would advocate the use of p-values for variable selection. That is not what they're for, not at all in any sense. P-values do one thing and one thing only, and that is they control the long-run error frequency of yes/no answers to yes/no questions given a set of assumptions. They have nothing to do with variable selection. So please don't throw all your variables into a model. Look for asterisks, throw out the ones that don't have asterisks, rinse and repeat until you have some set of variables that all have asterisks. It's not how you select variable. Another thing to use though, not to use, this is a little more sophisticated stuff here. These are powerful tools. AIC, BIC, cross-validation. These are powerful tools, kind of like smartphones. But even powerful tools have to be used for what they're designed for. Smartphones are not for opening beer bottles. AIC, BIC, cross-validation are not for selecting variables for causal inference. They are for optimizing out-of-sample predictive performance. If prediction is your goal, if you're predicting stock prices, if you're identifying images with machine learning, if you're a meteorologist, then fine. And there may be some very special cases where use of information criteria like this may be justified within a causal framework, but even that's debatable. These are not for choosing variables. They're not. Finally, this may be the one that hits closest to home sometimes. You should not choose variables based on what you or someone was or wishes to have been planning to include in the model before or maybe after seeing the results. All right? This is not how we choose variables. Now this sounds like it's almost like causal inference, right? It's almost like it, except not. It's like the psychologized version of causal inference. It's like Dumbledore trying to suck some memory out of his brain here. Don't torture yourself like this. You are not bound by what you or anybody else was thinking before the start of the experiment, except insofar as that determined what you measured and how you measured it. Okay. The reason we don't use any of these tools is that there are several things that variable selection is not about. Variable selection is not about optimizing variance explained. It's not about optimizing prediction. It's not about avoiding collinearity. It's not about getting the code to run without warnings. It's not about getting clean model diagnostics. It's not about statistical significance. It's not about streamlining your paper. None of these things should guide your variable selection. Variable selection is about one thing: getting unbiased estimates of causal effect given an explicit and validated causal model. It is about choosing variables so that you can say what happens when you move this slider up, what is the actual causal effect on the outcome. All right, DAGs help us do that. Let's practice. And this is where I hope what may have been too abstract the first time through becomes more understandable, because we're going to use variables that should be very familiar to everybody. Here we have land use, floral diversity, and pollinator diversity. Now, I should say at this point too, you may disagree with the DAGs I have drawn. You may think that a different causal structure is better. You may think other variables belong in it. That's perfectly fine. I'm sure you're right. I've drawn them just for illustration, so just believe the DAG for the sake of illustration, and then criticize it on your own. As we'll see, it's very important to criticize DAGs. But land use, floral diversity, and pollinator diversity, do you recognize the causal structure that's illustrated here? If the goal is to estimate the causal effect of floral diversity and pollinator diversity, what is the causal structure here of the covariate? Recognize it? It's a fork. It's a shared cause. What do we do with forks to get unbiased causal estimates? We condition on them. We include them in the model and thereby isolate the causal effect of floral diversity on pollinator diversity. And so our model might look something like this. I'm going to use kind of pseudo R syntax because I'm not a real statistician and I think about things in R syntax. Hope that's okay with everybody. Pollinator diversity modeled by floral diversity plus land use. Okay. Now, here's another example. We want to find, again, the effects of land use, but this time we're interested of the effect on the, sorry, these are the same variables, but we switched it around. Now we want to infer the causal effect of land use on floral diversity, but we also measure pollinator diversity. What do we have here? This is a collider. Isn't that interesting? Do you remember what happens with colliders? Right now, there is no causal information flowing through. There's no information flowing through that covariate because it's a collider. Just take my word for it. That's how it works. If we condition on it, though, that will actually open that non-causal path and it will bias the estimate we get of the causal effect of land use on floral diversity. And so in this case, the model is very simple. It is just floral diversity by land use. It doesn't matter what the p-value would have been. It doesn't matter what the AIC would have been. This is the correct answer, given the causal model. And finally, same three variables again, except this time, we're interested in estimating the total causal effect of land use on pollinator diversity. Notice now it has two causal paths. There's the direct path, and there's the one that's mediated by floral diversity. If we condition on floral diversity, we will block that causal path, and we will bias the estimate of causal effects of the estimated causal effect of land use on pollinator diversity. So we do not include floral diversity in the model. Again, it doesn't matter what the p-value or AIC would have been. If we do that, we will block this effect. This is significant. I chose this illustration for a reason. I won't name the paper, but there is a pretty prominent paper looking at the effects of land use of a certain kind on pollinator diversity. And the authors, one of whom I know and I like and respect, made a model that included these variables there was land use, there was floral diversity, and there was pollinator diversity, but they conditioned on floral diversity when the goal was to infer the effect of land use. What they ended up doing was probably blocking most of the causal effect of land use, because how else does land use affect pollinator diversity except via floral diversity? Well, maybe through nesting habitat, maybe through temperature, things like that, but probably the biggest one is through the floral community. And by including both of them in the model, you blocked it. You missed the chance to find the full causal effect. This is a published paper that has just an objectively biased estimate, and biased not in an anti-conservative way, but in an over-conservative way. This is the thing. This is not just about avoiding making overstated claims. That is part of what it's about. It's also about missing opportunities to make strong claims when we can. In this case, these authors missed an opportunity to make a much stronger and more accurate claim about the effect of land use of pollinator diversity. All right, bonus question. What happens if we have something like weather? And I'm talking about like daily weather, like how sunny it is the day that you went out and made your observations. It's not going to affect floral diversity. It's not going to affect land use, but it's going to affect pollinator diversity just because more pollinators are going to be active. What do you do when you have a causally independent covariate? Think about this for a second. See if you can reason through it. The answer is that if the DAG is valid, if our model here is valid, it's totally up to you whether to include weather. Including it or not including it will not affect causal effect that you infer for land use. You can include it and you'll get better prediction, but you'll get exactly the same estimate of the causal effect of land use on pollinator diversity if the DAG is valid. Okay. All right. Those are all pretty trivial examples. I want to work through this with a more serious example, a more intimidating DAG. Again, I'm trying to keep us in the topical realm of the Safeguard project, so this should be a familiar kind of question for us. Suppose we're interested in the causal effect of honeybee density on bumblebee fitness. Starts off pretty simple, but we can add some things to this DAG, and we probably should. One way that honeybee density might affect bumblebee fitness is through floral resource depletion, so we can add that. It might also affect it through viral load, so we should probably add this path too. Now, human density, like the population density of the area, probably affects both honeybee density via the number of beekeepers around, and bumblebee fitness through whatever, through temperature, through gardens, through pesticides, I don't know. But let's just say for this example that it does. And finally, let's say we measured honey production too. And honey production is caused both by how many honeybees you have and how much floral resource depletion happened. Again, let's just take the DAG as a given. What we can do to make causal sense of this DAG is dissect it into those fundamental causal structures and decide what to do about each one of them. What do we have here? Well, one thing we have is a chain. We have a chain here from honeybee density to bumblebee fitness via floral resource depletion. What do we do with chains? We don't block them, right? Don't block chains. Don't condition on the covariate in a chain. We have another chain from honeybee density to bumblebee fitness through viral load. Again, don't block the chain. Don't condition on the covariate. Up here, we have a fork. Human density is causing both honeybee density and bumblebee fitness. We do need to condition on that, right? This is now a confound. We don't condition on it, we will get a biased estimate. And then finally, down here, we have a collider where honeybee density and floral resource depletion simultaneously cause honey production. Don't condition on the collider or else you create a confound that wasn't there before. So what we get is this. We condition on on human density. We don't condition on floral resources, viral load, or honey production. And the final model is just honeybee density, is bumblebee fitness as a function of honeybee density plus human density. This is the correct answer for getting an unbiased causal estimate of honeybee density on bumblebee fitness. Make sense? Notice how logical all this was, right? There was nothing magical and incomprehensible about it. We didn't throw all this into an algorithm. We didn't use the dredge function. We didn't use forward or backward selection. We didn't calculate p-values. We didn't calculate AIC scores. We didn't use a random forest model. We didn't calculate variable importance and projection. Like, this is, again, as Richard McElreath always says, the causes are not in the data. You have to bring the causes to the data. And the causes that you bring determine the decisions you make about how to choose variables.
Sorry, Douglas.
Yeah.
Could you please explain again the different causal structures? It was fast a bit.
Yeah, okay, so
Thank you.
I'll explain them here. So the fork is when the covariate, in this case, human density. Do you see my pointer, by the way? Is that showing up?
Yes, I do.
Wonderful, okay. A fork is when the covariate is a shared cause of the treatment or the predictor and the outcome. A chain is when the covariate is a mediator of the predictor and the outcome. So the predictor causes the mediator, which causes the outcome. And we have two chains here. Floral resources and viral load are both part of a chain between honeybee density and bumblebee fitness. And then the last one is the collider, where the covariate is the common effect of two variables. In this case, it's not of the outcome, but of the mediator here. And if we condition on a collider, it becomes almost like a fork, but it opens up a source of bias that wasn't already there. The collider is one that's hardest to understand, and it's the sneakiest one. Now, to get all of these worked out, I highly recommend in the document that I sent you with readings, there's a paper called I think a crash course in good and bad controls. Rather than like trying to frantically write down all of these here, I really recommend just reading that paper because it goes through all this in great detail. I think the moral of the story here is if you started with this and said, oh, well, I want to do the principal thing and make sure I don't fail to account for any variables. So I'm going to model honeybee density as a function of floral resource depletion, human density, viral load, and honey production. And then you throw it all into a multiple regression model and you hope that somehow it all works out. That is a guaranteed way to get biased causal estimates of all kinds. In this case, you would have you have a lot of biases going on. Yeah, and similarly, if you did all that, and then you run the model, and oh, human density has a p-value 0.07, I guess I can drop it from the model. No, that will objectively bias your estimate. So yeah, the point is the selection of variables is guided by the causal logic of your system that you impose. It's not something that can be derived from the data by any kind of mathematical magic. That does not mean it is not accountable to the data. That's a different question. It is accountable to the data, and you need to hold your DAG accountable, and we're going to get to that in a little bit. Did I answer your question?
Yes, it does. Thank you.
Okay. So variable selection should be guided by causal logic, but not only variable selection. Also, by the way, if all of this felt a little hard to figure out, just imagine how hard it is when you have a much more complicated DAG, and they do get a lot more complicated. There's a wonderful website called daggity.net. I encourage you to check it out. The interface is a little bit clunky, but it lets you draw DAGs, and then you identify your treatment and your outcome, and it tells you what you need to condition on to get an unbiased causal effect. Importantly, I don't have a slide about this, but it's very important to say, there are DAGs that cannot be adequately conditioned. There are situations when you cannot get a biased causal effect with the measurements that you have. And sometimes you don't find that out. If you don't do this process at the beginning of the project, but just at the end, you may not find it out until it's too late to measure anything else, right? That's okay. You have learned something. This is something I'll probably talk more about on Monday, but we need to get away from this obsession with a certain kind of scientific success. Finding out that you cannot adequately condition a DAG is success of a kind. You learned what it would take to get an unbiased estimate, and you can still make your estimates just knowing that they're biased and reporting them as knowingly biased. Because you can say what biases them. You can say where the confound lies that you couldn't control for because you didn't have the measurements to do it. So, but DAGs don't just, and causal inference in general, they don't just guide variable selection. Also, very importantly, parameter interpretation. Let's focus on this again. I explained this this problem with the paper that I found, and we're going to revisit it here. So let's suppose that our goal was to get the full causal effect of floral diversity and pollinator diversity. We wanted it to be unbiased, so we of course include the fork there. The land use is a fork. We need to condition on it, so we get an unbiased estimate of floral diversity. Remember, so this the way a linear model actually works mathematically is it's an equation. We solve an equation. It's an equation for a line, so it's going to be an intercept plus a linear combination of slopes that are these slope coefficients, beta 1, beta 2, beta, etc., multiplied by each of the predictors, in this case, floral diversity and land use, plus some error term. All right, so this is familiar. So this is how linear models work. And what we're doing when we are estimating causal effects is we're estimating beta coefficients for the arrows between our variables. And the goal of doing this in a causally informed way is that our beta coefficients represent actual unbiased causal effect and not something else. So we set up this model to get an unbiased beta 1, an unbiased causal effect of floral diversity and pollinator diversity. Remember, this is like this mixing console. Beta 1 is one of these, or floral diversity is one of these switches, or a slider. So as we slide it up 1 unit. And what happens to pollinator diversity? It goes up or down by a beta 1, right? It's the slope. And let's say that these are the betas that we estimated for our model. This is the kind of thing that you would get if you call summary on your linear model and you look at the coefficients estimated, you'll get something like this. It doesn't matter for our purposes what the numbers are, but let's just say they look like this. And so what this means is that as floral diversity goes up, pollinator diversity goes up with a slope of beta equals 0.15, okay? You might think that this also means that as land use goes up, whatever that means, maybe it's, I don't know, urban land use, say. As urbanization increases, pollinator diversity goes down with a slope of negative 0.1. This is wrong. Can you see why it's wrong? Take a minute and look at it.
Should go up by 0.05, no? Or something like that.
Well, the problem is that part of the causal effect of land use goes through floral diversity, but we've not estimated that. We've blocked it by including floral diversity in the model. So we are statistically holding floral diversity constant at its mean when we estimate the effect of land use. But that's not a true reflection of the system because land use is a cause of floral diversity. And so the real effect of land use is going to be stronger than this beta 2. And this is the problem in that paper I mentioned, where they wanted the real effect of land use, but they conditioned on floral diversity. They blocked a chain and therefore biased the estimate that they got here. And so this is fine if the goal is to estimate the causal effect of floral diversity. This model does not work to estimate the effect of land use. So this is not a valid interpretation of this. If you wanted the full causal effect of land use, that's fine. Just take floral diversity out of the model. And this is another thing. This is like a change of way of thinking for us. You don't need just one model. You don't need to reduce everything to one model that answers all your questions. In this case, if you want the causal effect of both, you need 2 models. One model with only land use and one model with floral diversity and land use. This actually has a name. There's a whole paper on this called the table 2 fallacy. It's called the table 2 fallacy because very often the second table in a paper is a big table of parameter estimates for a model. And authors often interpret all of those parameter estimates as causal effects. And you know what I remember I said earlier about how part of the reason of doing causal inference in a principled way is because we eventually have to write something. I challenge you, go look at anything you've written, especially a discussion section. Look at anything anybody else has written. Try to find a discussion section that does not invoke causation in describing the results. I bet you won't be able to do it. And it's because we can scarcely think, let alone speak or write, except in the language of causation. That's just how our minds work. And so if we're gonna do that anyway, we had better get it right. And in this case, the problem is that people calculate all these coefficients and they think that all of them can be interpreted causally, but that's not true. Typically, only one can. Only the one that where the variables have been selected so as to isolate an unbiased causal effect for that variable. So I encourage you to read this paper. Maybe a little technical, but it's worth it. All right, now you're probably thinking, isn't all this a bit
Doug,
subjective? Yeah.
can I briefly ask, maybe you come back to it later than just say so, but when you decide on these models, one thing you are still free to do is like, if you assume, for example, there's a quadratic effect or not a linear effect, also for good arguments, you could just design the model with a quadratic term, you know?
Yeah. So that's a really good point, Thomas. DAGs are very agnostic when it comes to exactly what your model is going to be. And in a sense, that's a strength. Like they don't make a lot of assumptions, but at the end, I'm gonna talk about how that's kind of a weakness too. Like they another thing, and maybe even a bigger deal, is they don't tell you anything about interactions. And I'm going to talk about this specifically at the end. But yeah, it's not quite as simple. A DAG does not assume that everything is just going to be a first order linear model, Gaussian distribution, and all that stuff. There's still a lot of decisions to make, even if you have a DAG that you're happy with. And actually, that's a good segue here, because when should you be happy with your DAG? And a legitimate objection you might have at this point is, doesn't this all seem a bit subjective? Like, are you allowed to just draw any DAG you want, and then use it to guide your stats? And the answer is no. As I said, even though the causes are not in your data, the causal model that you produce has to be held accountable to your data. Let me show you how. DAGs have testable empirical implications. And in a sense, these are just the flip side of the causal logic that we used earlier to choose variables and interpret those parameters. So let's return to our more complicated DAG here. What this DAG says is it makes claims not just about where we can estimate unbiased causal effect, but it makes claims about conditional and marginal independence between variables. And so marginal just means two variables are absolutely independent. Conditional means that they're independent given conditioning on another variable. And so just to introduce this notation, this little like upside down T here means independent, and this pipe here means conditional on. And so this is something that DAGD will also help you do. It's a little tricky to intuit sometimes, but this DAG predicts that bumblebee fitness should be independent of honeybee density, conditional on floral resource depletion, human density, and viruses. It also predicts that depletion should be independent of human density, conditional on honeybee density. Depletion should also be independent of viruses, conditional on honeybee density. And human density should be independent of viruses, conditional on honeybee density. Okay, but how do we test these? And the answer is that each of these statements of independence can be reformulated as a linear model, or even something more complex than that, but let's just call it a linear model for now. And now the question gets reversed from our usual logic. We're saying that honeybee fitness should be predicted by honeybee density, depletion, viruses, and then humans. In this case, we're saying that if this DAG is true, there will not be a correlation between honeybee fitness and between bumblebee fitness and honeybee density if we have depletion, humans, and viruses as covariates. And so this may feel like a lot of work, but it's just, this is what you have to do to validate a DAG. You have to implement these models, estimate the correlation with its uncertainty, and decide whether the assumption of independence is justified. Now, you may be hoping for a little more cut and dry method than this. And unfortunately, methods like that do exist. But I think they're completely wrong. And frankly, I'm a little confused how it is that they persist in the literature, even in like packages written by legitimate statisticians. But what you'll often find is that people just run a bunch of like Spearman correlation tests on these models, and they check the p-values, and if the p-value is bigger than 0.05, they conclude that there's no correlation. That is complete nonsense, an utter abuse of what a p-value means. Actually, a perfect inversion of what a p-value is for. It makes zero sense. I'm sorry. Please don't do it that way. The best you can do is actually estimate this, just like this were a model that you cared about. Estimate it that way, and then decide, given the magnitude and the uncertainty of this estimation, is it justified to assume that these variables are practically independent enough for the DAG to be informative? And yeah, it's a little bit squishy in the end, but that's science for you. All right, I want to transition briefly to the limitations of DAGs, because as I said, I don't want you to walk away with the impression that this will solve all of your problems. It will help with a lot of problems, and it'll create some new ones, but these are problems you can learn from. One limitation is externality. This is a great paper from Richard Levins, a great man. I encourage you to read everything he wrote, including this paper. Remember those exogenous variables? We haven't talked about them. They're easy to forget about, but they don't go away. The things that you did measure were caused by things that you didn't measure. And what you don't know about those causes, you can't account for. DAGs don't tell you what's outside of your system. You choose the boundaries. And that's fine. We all have to do that. You have to choose boundaries. But don't forget that those boundaries are something you chose, and there's a world outside of those boundaries. And that world can include things that are confounding your estimates, and also things that would radically change how you interpret your results, especially in a case where some kind of intervention is desired. Another thing that DAGs don't do is this is not a problem with DAGs. This doesn't mess up your causal inference, but it just blinds you to something. And that is that between any two variables connected by what looks like a direct arrow, you could put an arbitrary number of mediators with an arbitrary structure of their own. Again, this doesn't bias your estimates, but don't forget that those are there, because it might blind you to something that you would intervene on if this is an applied problem, right? There are things between X and Y that mediate the effect of the former on the latter. And don't forget that they're there even though you didn't draw them. Another thing that DAGs, this is not so much a flaw of DAGs, it's just a limitation. They don't depict interactions. This doesn't invalidate the structure of your DAG or the way you're using it, but the fact that there's no good way to depict interactions in a DAG means that you're left to sort of figure that out on your own. What an interaction is when the value of one variable changes the effect of another variable on the outcome. So in this case, the effect of X on Y is not constant, it's dependent on Z. This is a troubling complication that we run into all the time in ecology, and like DAGs as such don't really help you sort it out because you can't draw interactions in DAGs.
Doug?
Yeah?
Maybe just a comment. I think it's important to kind of recognize that interactions of this kind are causal interactions, very different from our standard interactions in standard statistical models. So I see that there is a problem with that, but it may be much less important than in our standard statistical models, because I think it's much harder to imagine how causally Z would modify a causal effect of X and Y. I don't say that doesn't exist, but I think it's probably much rarer than that we find significant interaction terms in standard statistics.
Yes, I completely agree. And I think this highlights an important point that it's actually very hard to think to make causal sense of interactions. And in general, when I've tried to think about this, and I've talked to a friend who's also thought a lot about this, and the more you think about it, the more you're left feeling that anytime there's an interaction, there's something important missing causally from your model. And that's why you need to describe things in terms of an interaction. But that's about as far as I've gotten with how to think about interactions in a causally explicit way. I think the most serious limitation probably with DAGs well, one of the two most serious limitations is feedback. They're acyclical. That's in the name. Unfortunately, well, no, it's not unfortunate. It's just inconvenient for us. Ecology is full of feedbacks. And this, I think, really becomes a challenge of experimental design, that we need to understand what temporal complexities are at play. That's really what feedback is. It's a kind of temporal complexity. And we need to design our study and the temporal scale of our sampling and our inferences in a way that's very careful, so that the things that we're treating statistically, even the word statistics should tell you that it's not going to be good at handling time, right? It's about static things. There's very interesting etymology behind that. We can talk about that later, but goes all the way back to the Proto-Indo-European root language. Anyway, well, you need to design your study so that the things that are going on temporally are either happening so fast that you can consider them to be at equilibrium, or they're happening so slow that you can consider them to be constant. When things are patterned in time at the same scale as your observations, like in a predator-prey dynamic situation, any kind of consumer resource dynamics, you're in trouble. You probably need a temporally explicit model, probably some kind of a simulation, not a statistical model. And that's a good lesson too. And finally, look, you may have noticed that somebody's face has been behind here the whole time. Anybody recognize that fellow? That's René Descartes. A brilliant guy, did a lot of great things for the world, but unfortunately, he really got us off to in a bad direction by understanding the world as clockwork. Like for Descartes, the world is mechanistic. The world is like a clock. You can take it apart. It's fully decomposable. And DAGs are a formalization of this. DAGs presume that you can decompose your system into variables like this and draw them out, and that you can, it assumes that the world is close enough to a mixing console that you can move you can flip a switch here, you can move a slider there, you can take the world apart and put it back together. That breaks at a certain point, right? Like that can be useful, but it's not true, not in an absolute sense. This is something that Bill Wimsatt calls the causal thicket, where things are so entangled that this kind of a quasi-experimental approach simply can't make sense of it, because the moment you exert control over it, you're not measuring the same system anymore. You're measuring a kind of a facsimile of it, a simulacrum. Ecology at some level becomes a causal thicket. DAGs don't help you sort this out, but it doesn't mean they're not useful. So yeah, sorry, Descartes, the world is not a clock. It's not a mixing console either. It's important to remember that metaphors are only helpful until they're not. Okay, don't overextend them. All right, we've gone for an hour. I'm gonna conclude with the manifesto. And then we'll wrap up. I'm happy to stay and talk about this for as long as people want to talk. That's what today is about for me. But of course, I won't be offended if you leave. All right. Point one, we need a paradigm shift in ecology. This entails, first of all, understanding science as a study of causes, rather than relying on methods that were designed for optimizing prediction or something other than unbiased causal inference. This is what our goal needs to be. We need to abandon the alchemy of variable selection, right? We need to abandon baseless conventions, habits, sort of professional cultures of variable selection that are not grounded in any kind of rational logic. And we need to base variable selection and parameter interpretation on causal logic. Okay. And then this is the part that, this is actually a bit of a departure from what I've been saying so far, but it comes back to this idea of DAG validation, that we need to understand the crux of our work. The central goal of our research is the development of biologically plausible and data-consistent causal models. Because comparing alternative causal models is more important than estimating coefficients. A validated, biologically plausible DAG tells you so much more about the world than a slope coefficient, right? And we are so obsessed with individual coefficients and whether they meet some criterion of significance or whatever, that we forget that actually the more important thing is understanding the causal structure in which that particular coefficient participates. If you get the coefficient right and the causal structure wrong, you really haven't learned very much, and arguably you've just created more confusion. If you get the causal structure right, there's plenty of time to work out the coefficients, right? All right. Just a little teaser for Monday. We are gonna crawl out of the statistical cave a bit here, gonna bask in the light of the good. And we're gonna talk about how all of this causal inference stuff affects our workflow, what we actually do out there in the world, and very importantly, how we write papers. With that, I'm gonna stop sharing, I'm gonna stop recording, and we can have a discussion if anybody wants. Thank you.